Hello all. Now let us begin with the next topic, that is homomorphisms and factor rings. So first let us recall, what do we mean by homomorphism? We have two rings R and R dash, and let us have a map from R into R dash. If it preserves both the operations, that of addition and multiplication, then that phi is known as a homomorphism. So phi is known as homomorphism if phi preserves addition and phi preserves multiplication. So what actually happens is a homomorphism for rings relates both the structures, additive structure and multiplicative structure also. Okay, so homomorphism is nothing but a structure relating map, structure preserving, or we can say structure relating map. All right. Now let us move ahead. So we are watching projection homomorphism. What we mean by projection homomorphism? So suppose we are having R1, R2 up to Rn, and rings are there. Then R1 cross R2 cross and so on cross Rn. This will be the direct product of the rings. So it is itself a ring, as you know. And you define a map pi I. How we are defining pi I? So pi I carries this direct product into Ri. So pi I of R1, R2, and so on, Rn becomes Ri. So it is itself a homomorphism, meaning projection onto the ith component. So I would like to go with this example. You can see. I continue. So what do you have is, suppose R cross R cross R, I mean R cube. So I have X, Y, Z coordinates. These are Z axis, Y axis I have drawn now. And let us now draw the X axis from this point. These are X axis. So what you observe? Any point you handle has three coordinates, A, B, C, suppose. And let us suppose that you have projection pi and I'll say Z, pi Z, from R cross R cross R, R cross R cross R, in short we write as R cube, and to R. So what do I have? This gets projected to its Z component, and the Z component is nothing but C. So what I'll get? Pi Z of triplet ABC equal to C. So what I can say, this is just projection on XZ plane. Projection on XZ plane. So what is the value that I'm getting? The value is nothing but C. If you take its projection on XY plane, what will be the answer? Projection on, I mean to say, I'm sorry, it is on Z axis, I should say. So if I take the projection on Y axis, what will be the answer with us?
B.
B, of course, B. So I should not extend this. That was a mistake of mine. So I would like to correct myself. So this is our C. And the same way you can have projection on the x-axis, giving answer A over there. Okay. So this being 2D, I'm not able to draw it. But I think you can imagine the same thing we were discussing over here. If suppose you have R1 cross R2 cross and so on cross Rn, direct product of n rings, and pi I carries this cross product to Ri. So in that case, R1 belongs to first, R2 belongs to second, Rn belongs to the last one. And what pi I does? Pi I carries this whole tuple to simply Ri. So ith component is the answer. So this itself becomes a homomorphism. How would you say it is a homomorphism? How it becomes homomorphism? So I would like to go to the board then. So what do we have? R1 cross R2 cross and so on. And suppose I'm having cross R50 and you have phi, I mean pi I. So by pi I, let me say it is pi 11 from this cross product to, of course, R11. And if I'm having my vector as suppose U1, comma, U2, comma, and so on up to U10, sorry, 50 it is. What will be the answer under pi 11? It deals with the 11th component. So what will be the answer with you? U11. What we are doing, we are labeling the suffixes by the same letters. Suppose I have another vector V1, comma V2, comma dot dot dot. Last is V50. I suppose you are getting, so it is a member of this cross product, direct product. And I apply this pi 11 on this. So what will happen? What will be the image? Yes, have you got the concept? What will be the image? Are you not getting my point? I'm not able to listen to you. Yes. No one knows the answer. Priya?
Repeat again.
Okay. Okay. See, we are saying pi 11. What 11 indicates? It indicates that we are getting component on this particular 11th thing. So what you observe here, R1 cross R2 cross and so on cross R50. This much cross product we have. What I mean by cross product, I have that many tuples, that many coordinates with us. And you are taking pi 11 projection on the 11th set. So you'll get the 11th component directly. If you operate it on this particular coordinates, you'll get the 11th component directly. So what will be the output of this?
V11.
Yeah, of course, it will be V11. It will be V11. All right. Now, if suppose I had a total, I mean the sum of these two, meaning first place U1 plus V1, second place U2 plus V2, just a minute, U2 plus V2, and so on. What will be my last component here?
U50 plus V50.
Yes, U50 plus V50 I have. This is the sum of these two, I mean vectors. And let me apply this pi 11 on this. What will be my output? Expected output.
U11 plus V11.
Yes, the 11th component that comes up to be U11 plus V11. So what is U11? U11 is the output of this pi 11, isn't it? So what I have got? Pi 11 of this particular whole thing. Let us denote it by U bar. Let me denote it as U. So pi 11 of U, I can say so. Just a short form. and this I'll read as V. So I'm getting output of pi 11 operated on V. Okay, so can I say this is U and can I say this is V? Got me? What was this? This
Yes,
was
ma'am.
pi 11 of U plus V. This is our vector U plus V. I suppose you're following me. What we did, the two members of the ring, we added, U and V, we added, and we applied our pi 11 on it. So what pi 11 does, it gives simply 11th component. So we got our 11th component, that was U11 plus V11. Is it okay? And U11 itself is the output of pi 11 of U. And V11 was the output of pi 11 of V, as you are watching over here. So you can see this particular pi 11 preserves addition. Same way you may have pi 10, pi 19, pi 49, any. It ranges from 1 to 50 for us. Got me? Okay. Now let us discuss what happens in case of multiplication. So let us go with multiplication. So how do you define multiplication in case of this Cartesian product? If at all you are having, I think it is not properly visible. Okay. So you have R1 cross R2 cross and so on up to R50. And suppose you are having your vector U bar and V bar and you want to talk about their product UV. How do you define this product? Product goes component wise. First component into first component, comma, second component into second component, comma, and so on. The last component into last component. Do you remember this? This product goes very component wise. And now you apply your pi 11 on this. What is to happen? This will be pi 11 operated on this particular. What will be your output? Yes, please come on. What will be the output? Of course, the 11th component. What is your 11th component?
U11.
Yes, into V11. But U11 is the output of what? Pi 11
I11.
operated on U. And what is V11? It is
I11.
operated on V. So you can see image of the product is product of the images. Do you agree with me? Image of product is product of the images. And in the uppercase, what you saw? Image of the sum is sum of the images. Do you agree?
Yes, ma'am.
That is why what you observe is pi 11 satisfies both. It preserves addition also and it preserves
Multiplication.
multiplication also, and that is why it is a homomorphism. So I think you got the concept of what is homomorphism. I have already shared this to you. Okay, so I hope there is no problem in understanding this. Sure. Do you want this in written? How many of you want this in written? Let me know. Jyoti, you want in written?
No, ma'am, I've understood.
Okay.
Ma'am, can you please share yesterday's PDF that you
Actually,
shared?
actually, I have PDF. Which one? That I downloaded from the net.
Yes, yes.
Okay, I would like to. Sure. All right. So shall I proceed then?
Yes, ma'am.
Okay. So we talked about what is projection. So projection is just that particular component we are taking, keeping rest as they are. So in this particular case, if I talk about pi 2 operated on R1, comma R2, comma and so on up to Rn, what will be the output? What will be the output? Yes. What is this? Pi 2. Pi 2 means second component. What pi 2 refers to?
R2.
Second component. So what it should be? R2. Are you getting my point? So the way we find projection on x-axis, projection on y-axis, likewise here we have n components where you are taking projection. So if you are taking projection on second component, your answer will be second component. If you are taking projection on 100th component, it will be R100. Followed my point?
Yes,
Okay.
ma'am.
Okay. Let us go ahead then. See, there are few properties of homomorphisms. So let us deal with the theorem. See, phi is a homomorphism of a ring R into ring R dash. If 0 is the additive identity in R, then phi of 0 is 0 dash. 0 dash is the additive identity in R dash. So what do we mean by this? If we are having R and here I'm having R dash. So in R I'm having additive identity 0. Here I'm having 0 dash. So phi carries 0 to 0 dash. Okay. Then if suppose I'm having element A here in the ring, its additive inverse is always minus A. So if I have image of A as phi of A, then image of minus A directly goes to minus of phi of A. If image of A is phi of A, then image of its negative is negative of its image. It is so easy. Phi of minus A is the same as phi minus of phi of A. Phi of additive identity is the additive identity. So it is so. Then, if S is a subring of R, have you understood these two concepts? Identity, additive identity goes to additive identity, and negation, I mean negative, goes to the negative of the image. Did you follow me?
Yes, ma'am.
Okay. Okay. Then let us go to the concept of subring. If suppose S is a subring of R, then phi of S, image set of that particular S, also is a subring of R dash. So whenever S is a subring, phi of S is also a subring. But what is phi? Phi is not ordinary map. Phi is a homomorphism. Phi is a homomorphism. Okay. So you said your S you selected from R. If you take S from R, you get phi of S in R dash. Phi of S is also a subring. Now the question comes, if I have on the contrary, if suppose I select some S dash from here, its inverse image, how it will be? Inverse image of S dash, how it will be? Will it be a subring again? Yes, surely. So you can check over here the concept. If S dash is a subring of R dash, then phi inverse of S dash is a subring of R. J, direct image of a ring is also a ring. Inverse image of a ring is also a ring. We are talking about subring, but to be a subring, it should be itself a ring and a subset. Then we call it a subring. Followed? Okay, I would like to once again rewind it. Okay, but before rewinding, I would like to just a minute. Okay, so once again, let us come to the point. Say you have phi as your homomorphism. What is meant by homomorphism? A map from a ring R into a ring R dash, which preserves both the operations, preserves addition also and preserves multiplication also. That is known as homomorphism. So our theorem talks about a homomorphism. This is a homomorphism. Okay. What it says? 0 of R is carried to 0 of R dash. So 0 of R dash we are denoting by 0 dash. So image of 0 is equal to 0 dash. So if 0 is the additive identity in your parent ring, then 0 dash is the additive identity in R dash. Next point, for every A belonging to R, phi of minus A goes to minus phi of A. I would like to read it as image of the negative is negative of the image. I repeat, image of the negative is negative of the image. So as you are watching, A goes to phi of A. So minus A goes to minus phi of A. I suppose you followed it. Sure? Got this point? So additive identity goes to additive identity. Negative of an element goes to the image of, negative of the image. Next point comes is of subring. If S is a subring of R, then image of S is also a subring of R dash. I repeat, if S is a subring of R, image of S is also subring of R dash. Now reverse way. If S dash is subring of R dash, then its inverse image, phi inverse of S dash, is also a subring of R. I suppose you are following all those statements. Lastly, if R has unity, a ring may have unity, may not have. So if your ring R is having unity, then phi of 1 is unity of phi of R. I repeat, I would like to highlight it again. If R has unity 1, then phi of 1 is unity of phi of R. So loosely, what we can say, subrings correspond to subrings and rings with unity correspond to rings with unity under a ring homomorphism. Followed it? And that is why the word homomorphism is used. What the word homomorphism indicates? You get the same kind of structure. That is the meaning of homomorphism. So proof to this theorem I would like to share in written, so that I'm sharing to you. Okay. So let us proceed. Now we will handle our most important definition, that of kernel. Definition of kernel. So what is kernel? Kernel is the set of all elements in your domain whose image is zero, whose image is additive identity. And this is actually familiar to you right from vector spaces. In case of vector spaces, we used to say kernel of T. I suppose you remember it. Last year you have done it. Kernel of T is the set of all U belonging to V such that T of U is zero. Have we done this? So in vector spaces, you have learned this kind of thing. How many of you remember? None? Okay, very good. All right, I would like to repeat the definition for you. Doesn't matter, but whenever you learn things, you just go on updating yourselves. It's an important thing. Once you learn a thing, that is actually a step to proceed ahead. So never forget the things. These are important things. By kernel, what we mean? Those elements which are mapped to zero, that is known as kernel. So in this case, you have phi as a homomorphism from R to itself. Then we have the set of all R belonging to R whose image is zero dash. If you have so, then what you'll say? This is nothing but the set of all R. See, suppose I draw a Venn diagram, something like this. This is my R and this is my R dash, let me say. What I have few elements here. These elements, shaded portion. All of them, they are mapped into a zero here. And zero in R dash we denote by what? Zero dash. So all those elements that are mapped into zero dash means they have image under phi at zero dash. So those elements, they form kernel of phi. The set is denoted by KER of phi. Are you following my point? This much you got. What I said? I have few elements which are mapped into zero dash under phi. Did you follow this statement? Okay. Okay. All right. Okay. See, you have two rings. One ring is R, the other one is R dash. And you have a homomorphism from R to R dash. That's it. So what we will do is, we will see how many elements are there or which elements are there whose image is zero dash. So let us collect all those elements. This particular shaded portion is known as kernel of phi. Why I have shaded it? Because these are those elements R whose image is zero dash. Okay. So speaking in reverse manner, what it means? They are all inverse images of zero dash. They are all inverse images of zero dash. So I can write this as what? Phi inverse of square bracket zero dash. What this indicates? all inverse images of 0 dash. Whatever members are mapped to 0 dash, all I'm collecting under a set, and that set is labeled as kernel of phi. Followed me? Okay. All right. So I would like to go to one example that will make it more clear. Hope you are familiar with this example, 37th one. Are you? How many of you remember this mapping? How do you know this? Yes, this was asked in your exam. Okay, so let us see what is kernel of this particular. Let us check what will be the kernel. So inverse image of zeros. So I want this to be 0, 0, 0 and a 0. So what will be your A plus BI? So that all those elements will be zeros. Come on. Pradnya? Come on. I'm not able to hear you, beta. Anjali. Don't know what has happened, but I'm not able to listen to you. Yes, anybody? Whenever you are inputting, suppose I input 3 plus 2i. In that case, what is its image? If I input 3 plus 2i here, what will be the image? Huh?
3,
Yes, of
3,
course,
2,
3, 2
2,
minus 2i.
minus 2, 3,
Very good.
3.
Very good. So knowing A and B, you can tell me the matrix. Now knowing the matrix, can you tell me what will be there? What will be the input? Yes. If I tell you, like my matrix is something like 5 minus 6, 6, 5. So it is the image of what? Yes, help me. Image of
0 is in 0.
yes, you're right. You're right. You're right. But in this case, now help me.
5 minus 6i.
Yes, very good.